Cool. All right, so this is the last lecture of this platform security module, and we're going to start talking about software security next time. So it should be fun because today it's going to be essentially a case study of iOS, iPhone security. And we're going to talk about the same things we've been talking about throughout this module, things like application security, where you get the applications from, secure boot, file encryption. I guess that's new. But we're going to see it in the context of a particular system. This iOS security story is very well thought out. If you buy a modern iPhone, there's a ton of security protections and thought that went into setting it up. So I'm going to try to give you just a sliver of that, a taste of what's going on. And I think this is, I guess, also an opportunity for you to ask questions and understand better some of these concepts that we've seen already, but that might be easier to understand a second time. And then the last thing I'll do is talk about some of the attacks. So when we're thinking about secure system design, secure boot, once you see how it works, it might be hard to see how can it break. It seems like such a robust way to get booted into a known good operating system. What can go wrong? So I'll try to cover a bit of that too. So any questions? Any questions before we get started? Thoughts? No. All right. So I guess the first thing I wanted to do, just to get us thinking, is when we're talking about crypto or even sometimes about systems design, typically we're starting with like a tiny piece of the problem, and we'll think about how to solve that. So we'll think about, I don't know, two parties share a secret. How can they exchange messages over an insecure channel? When you're designing an iPhone, you have this. You're Apple. You're designing the iPhone. You're not thinking kind of about the small problem going out. Often you're thinking about what are the attacks that I'm trying to prevent, and then coming up with a bunch of different strategies to address those issues. So if you're Apple designing an iPhone, what are the kinds of attacks that you might worry about? What are the security threats that you want to design against? Yeah. People jailbreaking. So can you say one more sentence about what that means? Yeah, exactly. So why would Apple care about that? So they want to control the OS experience. That's kind of a, why do they want to control the OS experience? Yeah, so it depends. That you seem like a glass half full type of person. They're trying to keep you safe. They're trying to make sure that you're not running apps you shouldn't run. Anyone? Do we have a glass half empty person? Yeah, exactly. So does anyone else know why they might not want you to run apps, unapproved apps? Yeah. Yeah, so you'll buy apps from the App Store. So I should say jailbreaking. This is like run your own OS on an iPhone. You buy unapproved apps from the App Store. I guess we'll come back to this, but so you're depriving Apple of revenue. You're also depriving them of control, right? When they run the App Store, they get to decide what's a good app and what's a bad app. I'll come back to this in a second. But I think one of the themes that's really interesting, and I guess it comes up all over the place, but particularly with the iPhone, is sometimes these security protections are designed to protect Apple's business interests, and sometimes they're to protect your business, your interests, and indirectly Apple's business interests. So obviously, if the phone is good, you'll want to buy it. That helps Apple. But sometimes it's much more direct. Like you'd like to jailbreak your phone, but doing that is going to cost Apple money, and so they want to prevent you from doing it. So I guess when we're thinking about these security protections, whatever they are, you should be asking yourself, just be aware, whose interests are these protecting? Is this for Apple's security or for my security? And it's not, sometimes it's blurry, but it's just worth keeping in mind. Cool. What else could you care about? Apple might care about in terms of security threats. Get a new person, yeah. An app pretending to be like the OS. So I don't know where we'll put this. Yeah, so kind of phishing your PIN. This is Nikolai talked about secure attention key, which is on I guess the older phones. you would push this button to log in, and if there was an app that was trying to phish you, that app would get sort of disappear as soon as you did that. So that's definitely a threat. What else? What else might Apple care about, security-wise? Yeah.
I guess maybe hardware.
Yeah, yeah. Now I'm gonna run out of space. So let's see, hardware. So this is a device that you're using. Yeah, so maybe let's say counterfeit devices, something like this. Is this what you're thinking of? So when you go to the store, I think that's how you spell it, devices. So when you go to the store and you buy an iPhone and you turn it on, Apple wants to somehow ensure that you're running a real iPhone and not some stolen one. Yeah, what else? Let's get a couple more new people who haven't spoken yet. Yeah. Yeah, absolutely. So I'll put this in kind of application category. So say I'll call it malware, which is, spying on you, stealing your contacts, etc. Definitely. What else? Yeah, one more maybe. I'm going to wait for a new person because I know there's a few of you who haven't spoken yet. Could be anything. Yeah, do you have an idea? Yeah. So this could be, an app a bad app that you install, maybe hijacks your OS or something. Or, all sorts of badness could happen there. I guess a couple that we'll talk about today that aren't on this list. So we'll talk about jailbreaking. We already talked about this, so I'm not going to. I'll talk about, apps that can tamper with your OS, sort of secure boot addresses that. The other one is, you may have heard about in the news, is you leave your iPhone in a restaurant, somebody picks up your iPhone and wants to get your data off of it. Yeah, it could be a law enforcement agent, it could be when you're crossing a border, international border, or it could be a significant other who's kind of semi-malicious, who wants to see what's on you. Not a joke. This is something they think about. So cool. So let's start with talking about application security. So, and this is going to be kind of on this first thing, how, what does Apple do to protect against malware, or what techniques are used in the iPhone? So of course, the most secure computer or phone that you can use is one that doesn't actually run any software on it. Like you get it in the box, you leave it at home, you don't do anything with it, perfectly secure. But this is, not very useful. So for your phone to be useful, you have to download these apps, and these apps are going to be written by random people on the internet who you don't particularly trust. So this is kind of, I think the source of all computer security problems is someone tries to do something useful with a computer, and typically that's downloading software from a random person and running it. So I would say there's kind of different ways of different systems handle this differently. And one way to think about it, that I'm not sure if this is the best way to think about it, but in the context of iOS is the following. If you, think about a platform or the way that you get applications onto a device and run them, there's kind of two different types of, or like 4 different types of platforms you can think of in quadrants. So one is like how much access to sensitive data does an app have when it's running on this platform? So I would say, for example, if you're running an application on your iPhone, it potentially has access to your camera, it has access to your contacts potentially, it has access to your location information, all sorts of sensitive stuff. So I would say, whereas if you're running an application in your web browser, you haven't logged into anything, it doesn't have access to that much stuff, right? Unless, this is breaking down where you can grant more and more access. But typically, you visit a random web page, it can't get your location easily. It can't get your photos easily. So I would say, phone apps are definitely dealing with more sensitive data. The kind of other dimension for a platform that I think of is kind of openness. So who can write an application? Anyone can write a web page. You will visit that web page. You will download some JavaScript. Your browser will run it. So basically, anyone in the world can run code on your computer if you're running a web browser and you visit their web page. That's not so true for the App Store. So I'd say, I would put kind of web application or websites, JavaScript over here. Something like the way your normal Linux machine is up here. So when you download software on a Linux machine, you install a package with your favorite package manager, you're downloading software that some random person on the internet wrote, you run it on your machine, it has access to your files, it has access to all sorts of stuff on your computer, but anyone can write software for your Linux machine. So I would say these are like more open and varying levels of access to sensitive data. And I would say kind of the iOS world is over here, where if someone's running an application on your phone, they potentially have access to a lot of sensitive data. But Apple's strategy is to kind of lock down who can run software on your phone to try to get more security that way. So what happens with iOS? Has anyone actually written an iOS application? Oh, awesome. So some of you know this. So what happens? How do you get an iOS application into the App Store? Do you know? Yeah, exactly. So you have to get a developer account, which Apple can revoke if they you do something that makes them unhappy. You have to sign the binary that you submit to Apple, and then there's some App Store review. Yeah, just to kind of make the point I'm trying to make here. When you write a website, you just write the JavaScript, you put it online, anyone can visit it. You don't have to get a developer account, you don't have to sign a binary, nothing. Whereas with the App Store, there's actually quite serious, in many cases, manual human review that goes on. So there's kind of two reasons for this. The two reasons that we were talking about before. One is to protect you from malware, right? Where Apple wants to make sure that someone can't write kind of flagrantly malicious app that say gathers all your contacts and sends them out to some server that's going to do some nefarious thing with them. The other thing they do is check that the app isn't making Apple's business lose too much money. So for example, if you make purchases through the App Store, so if you have an app, say I have an app for I don't know, photos, and there's filters that cost money, Apple takes a 30% cut of anything that you buy through the app. And so they want to make sure that your app isn't kind of circumventing their money-making strategy. Yeah? It's some of both, but it's surprisingly manual. So I think there's some, and Nikolai may know more than me, but I think there's some sort of checks that the permissions you're asking for, I'll talk about in a second. You have to declare whether your app is going to use the camera or not. And there's some, I think, kind of very simple automated checks to check, okay, if it's a note-taking app, it shouldn't need the camera or something like this. But then there's quite a bit of human review to make sure you're not using Apple branding in your app and this kind of stuff. My sense is the scrutiny that happens here increases dramatically with how much money your app is making. So if you're making a lot of money, all of a sudden they're going to start paying attention. Yeah, the other thing that's interesting is if you look at Apple has so they have a nice policy about what gets through the App Store and what doesn't. And the policy is basically whatever we feel like today. So it's very, very arbitrary and can change anytime. So this is why it's somehow, you get some security, but you pay something for it. So for example, you can have an app store that offers personal loans, but not if the percentage yield, the rate of interest is over 36%. So these are kind of you can offer personal loans for 35%, but not 36%. So stuff like this, where it's I don't know if this is, you can sort of see the justification. They don't want you to be kind of loan sharking people with the App Store, but at the same time, it feels, if you like free software, this should make you work. Okay. This is not the technical stuff. So I'll get to that in a second. So any questions about that? People know this is how the App Store, yeah. Yeah. Let me say something about that right now. So there should be kind of an asterisk here. This is, maybe I'll call this like potential access to sensitive data. And iOS actually has a much better story for this than, say, the binary running on your Linux machine. So each app on your phone runs in its own sandbox. So the picture is very much like the one that Nikolai showed when he was talking about isolation, where you have these apps, they're all running. These are the apps. And this is kind of the iOS. They're all running in their own sandbox. They have their own home directory. They don't share files with each other. The only communication, inter-app communication, is via, iOS APIs. So, for example, you can click a link in one app, and that will open a web browser app. But that's only through special APIs. And when you create the app and submit it to the App Store, you have to declare which APIs you're going to use. So the app must pre-declare which APIs we'll use. And Apple, when they put your app into the App Store, basically restrict your app's ability to call these APIs to whatever you said it was going to call. So for example, if you have a weather app, the weather app won't be able to access your camera. Presumably, if Apple's paying attention, they will not approve your weather app and put it in the App Store if you're asking for the camera, unless there's a good reason for it. So this is a pretty nice protection, and it means that if you're running an iOS app and it shouldn't have access to the camera, it's going to be very difficult, short of kind of breaking out of the sandbox, to get access to it. So this is another way in which, if you're running a Linux machine, you don't really have this. There's no one sort of doing this fine-grained control over which pieces of your system each app can touch. So things, APIs that that apps can use, they can say control the network settings or not. So there's VPN apps that companies, corporate people want to use. Location, all the things that camera, all these things you kind of have to pre-declare. And Apple will try to limit kind of your app's access to these things to get before an app ends up in the App Store. So this is one way in which the security story for iOS is pretty nice. So okay, now that we've talked about how that works just at a very high level, I want to talk briefly about where things can go wrong, unless there's a question about this. Oh. So okay, so what can go wrong? And I guess it's kind of hinted at one thing that can go wrong, which is, Apple is a capricious dictator, and they can pull your app from the App Store if they don't like it. But I'm more talking about security kind of malware issues here. So at the start of the semester, Nikolai mentioned this thing called Xcode Ghost, which you probably will not remember. But what happened is when you're a developer and you're building an app, you compile it with something called Xcode, which is a set of developer tools. And Xcode is a very, very large piece of software, sort of gigabytes to download. And in China, there was someone posted on a Chinese mirror a version of Xcode that was backdoored. And so what this backdoored Xcode compiler would do is it would compile your app, it would look fine, but it would insert some extra stuff into your app without asking you. And because this developer tools was so big, people in China were downloading it from the mirror instead of from Apple's official sources. And they were producing iOS apps that were backdoored. Yeah, so what happened is when you compile your app with Xcode Ghost, there's extra features. And there's some speculation that this was an intelligence agency that did this, but as far as I know, nobody really knows who is behind this. So, okay, so first point that this shows is that the App Store review didn't catch this. So this App Store review is really imperfect. Yeah, so you shouldn't think of the fact that Apple gets to look at your app as meaning that there's no malware in the App Store, because of course Apple can't really scrutinize every app with the level of detail that they would need to. So one conclusion is the App Store is imperfect. The second thing, or I guess another thing to learn from this that's kind of interesting, which is different from these other cases, is the App Store this App Store model was extremely helpful at remedying this after the fact. So once someone realized that this happened, Apple can go back, they can look at all the binaries on the App Store and figure out which ones are backdoored by essentially grepping through the code for certain patterns. Then they can pull those apps from the App Store, and in fact, tell people's phones the next time they connect to the internet to wipe that app. So in terms of, I'd say imperfect, but helpful, super helpful for cleanup. Cleanup after the fact, right? Because on the internet or random binaries you download from the like nobody's going to help you. Yeah.
Why do they do that? Like we were talking about before, like it's hard to verify like the content of the binary kind of like you can't relate it to the source code. Why don't they just have you submit the source code and then Apple?
I don't know the answer to that question. My guess would be that you might not want to submit your source code for kind of intellectual property reasons, but do you know, Nikolai?
Their tools like don't have probabilistic builds as far as I understand it, so can't really sort of verify that they match. As to why they don't build it for you, my guess is indeed there's lots of things you might have in there. Sometimes your code has assembly because you need high performance, and you have to jump out of there sometimes. I don't know what the deal is. Like you have copyright code that you don't want to give to Apple or private code. I don't know.
Yeah. Good question though. Okay, so yeah, helpful for cleanup. Unlike, because it's so centralized, it's kind of, usually how a dictatorship works. Some things are more efficient, but if you're on the wrong side of the dictator, then you're in trouble. So I would say that's one benefit here. And they did pull a bunch of apps. The other thing you could ask is like, if the isolation is so good, why do we care? Why do we care? Why do we care if someone put malware in one of our apps on our phone? It's in its little sandbox. It can't do anything. So just to get you thinking, why do you care still? The app is perfectly sandboxed. Yeah. Yeah. So definitely if it's your banking app, right? Or So maybe if it's a flashlight app, you don't care. But say if it's a banking app, then it's going to get your financial information. Maybe it's an app that takes a credit card number, then it's going to get your credit card information. I guess there was an instance of something called Fake Tor, which was an app in the App Store for a long time that pretended to be the Tor browser, which is a kind of privacy-preserving web browser we talked about. So there, it's going to learn which websites you're visiting. So if you're putting kind of sensitive data stuff into this sandbox thing, it doesn't matter if it's sandbox. You're still kind of giving it data that you don't want it to have. There's another problem too, which is a sandbox that doesn't talk to anything else is not a very useful. An app that can't talk to anything else not very useful. So there's a lot of ways in which apps can communicate with each other, and that can also cause problems. So for example, there's a copy paste functionality in iOS and Android, or basically any computer system that you use. And if you're using, say, a password manager to copy a password and then paste it into a web browser, that exposes, depending on how things are set up, could expose the password to any app that's on your machine that can read the clipboard. And in fact, this Xcode Ghost app was able to read the clipboard, and so could maybe like steal your passwords from your password manager. So there's like two reasons: sensitive data coming in, and then there's actually some sharing between the apps. Still, having said all of that, this isolation buys you a lot. The fallout from, this kind of attack, where it's like all it can do is copy paste stuff from the clipboard, is much, much less severe than what would happen if you ran a binary on your MacBook that was trying to do something malicious to you, where it could read all of your files and ship them out over the internet. So okay, that's what I wanted to say about malware. Any questions? We talk about secure boot. Is this an iPhone crowd or an Android crowd? I don't know. Do you have iPhone users? Any? Oh, half. Okay. I see a lot of iPads too. This is basically the same thing. So, okay, let me now talk about secure boot and then get into the sort of encryption of data at rest. So this is really to address the jailbreaking issue, which is someone installing a non-Apple OS on an Apple device. So the goal here is make sure your iPhone runs an Apple-signed kernel. So this protects against people installing different OS on their own phone, or you leave your phone in some place. I guess really jailbreaking is the biggest. If there's encryption things that prevent someone from switching out your OS while you're not looking. It also protects against malware that gets on your phone that somehow escapes the sandbox and corrupts the OS. The next time you boot up, you can be sure that the correct OS is running. So the way this works in the iPhone is there's kind of 3 steps, which is similar to what Nikolai mentioned. There's something called the boot ROM, which is a very, very small piece of software that cannot be changed. This is cannot be updated or changed. It's like burned into the hardware, the boot ROM. And what happens when you boot the machine is that the boot ROM loads, it has a public key for Apple in it, some kind of PK Apple. It reads in this what's called the low-level bootloader. It checks a signature from Apple on this bootloader, and then the bootloader starts executing and executes checks a signature on the kernel, and then executes the kernel. So it's kind of a 3-step process where this thing, some people call the hardware root of trust, including Apple's public key, is burned into the phone. So if at any one of these steps there's a failure, say the signature fails to verify, the phone kind of boots into this recovery mode. And the presumption is if some malware has escaped the sandbox, has corrupted your OS, what you need to do is reinstall your operating system. And so that's how you end up in recovery mode. So this is what trusted boot does. And this is very similar to what Nikolai described. So I guess rather than just, this is all it is. I don't know if anyone has a question, we can talk about it. But I want to discuss, there's a lot of jailbreaks of iPhones where people can run their own operating system on an iPhone. And so I kind of want to explain how that can happen. But before I do that, are there any lingering questions about secure boot? Everybody did well in the midterm, so and now I'm going to just assume that you understand what I'm saying, unless I hear otherwise. So good. So let me explain where things can go wrong. And as always, the enemy of security is functionality. And what sort of happened, one way you can think about happening is if you try to jam too much stuff down into the lower levels of this process, you get into trouble. So you could say, why do we need 3 steps here? Why doesn't the Apple just burn the kernel into read-only memory, or a hash of the kernel into read-only memory, and then we don't need to check any signatures at all? It just, boot up, read the kernel in, check that the hash matches the hash that's in the boot ROM, and then start executing. So why don't we do that? Why not burn a hash of the kernel into the boot ROM? Yeah? You can never change the kernel. Why would you want to change the kernel? Yeah, but you can never change the boot ROM. So even if, so I agree with you, never being able to change the kernel would be bad. But now we have the situation where you can never change the boot ROM, which has Apple's public key in it and loads a bootloader. So what happens if Apple loses their secret key? This is not a. Yeah, they might still be useful as frisbees or. No, I know. I mean, they'll probably still run, but they'll be buggy. They'll be in big. So if you have bugs down here, you're in really big trouble. And so you want to make this thing as small as you possibly can. And this thing should also be small, but these kernel can be as big as you want, right? Sort of, because then you can always change this stuff. But down here, this cannot be updated. So if there's bugs over here, there's gonna be a bug forever until your phone dies. So one of the ways that you can jailbreak a phone is if there's a bug down here. So let me just explain how one jailbreak works. Break works. And the one I'll describe is this sort of simplified version of a relatively recent one called checkrain that's spelled like that. So what happens is this boot ROM, it actually has to do some stuff. In particular, one of the modes that one of the features that this thing has to support is if your phone gets into some really bad state and you need to reinstall, you need to kind of reinstall the bootloader and the kernel from your laptop. So you plug the phone into your laptop and you boot it up into some recovery mode and you upload a new image of the kernel and bootloader that is clean. So this thing actually needs to speak. This thing needs to speak USB, so that you can connect it to a laptop to recover from your computer. And so the problem is that speaking USB is not so easy. Not so easy. There's actually a lot of code. What happens when there's a lot of code? A lot of bugs, right? So this is like bugs. So what happens is when there was a bug in this boot ROM for Apple, I guess up to A10 devices, so many iPhones, where if you plugged a USB cable into it and into a laptop, you could trick the phone into executing arbitrary code that you feed it over USB. So this boot ROM, rather than checking a signature on anything, you would kind of catch it early, you would feed it an image of a binary that you wanted to run, and then you would, by a clever sequence of kind of use after free and type of attack, so memory errors, you could trick the boot ROM into executing whatever code you decided to give it. So, get arbitrary code execution via memory, like a memory error. And now the problem is you can't update the boot ROM. These phones are jailbreakable forever. So basically the bug exists forever. But the good news is that as soon as you reboot the phone, this boot ROM goes back to this boot ROM never changes. So the bug is still there, but you would have to re-execute this attack every time you booted the phone if you actually wanted it to stay in this weird state, jailbroken state. There's a clever patch on more recent iPhones that I'll mention at the end if we have time, where they were actually able to defend against this attack, Apple was by using sort of a surprising and clever strategy. But okay, that's just all I wanted to say about secure boot. Does it make sense? Surprising? Not surprising? Has anyone jailbroken an iPhone? You have. How were you successful? Check rain. Nice, nice. So this is all like intimate. I was reading about some of these attacks. They're extremely, extremely intricate. You could jailbreak your iPhone from a web browser. Like you just open a page in Safari and boom. That's terrifying. That's terrifying. I did not know about that. That's yeah, these things you go back to using pen and paper after you learn about these types of attacks. Okay, so the next thing I want to talk about for part of the remainder of the time is this one attack that we didn't list here, which is what happens when you leave your phone at a restaurant, somebody picks it up and wants to get the data off of it. So the ideal is that if the attacker doesn't know your PIN, it's not going to get anything off of the phone. And that actually turns out to be pretty difficult to achieve. But the story in iPhones, and similar thing in kind of some Android phones, but modern iPhones do it quite well, it's not that easy to do. So I want to talk about okay, so you have an iPhone, you have some data on it. You want to protect the data that's sitting in Flash. We've studied cryptography. What do? It's like the first thing that comes to mind is encrypted. Yes, I know you all did well in the midterm, so I'm sure, yeah, you encrypted. So you could imagine taking a 128-bit AES key. You take each file, or you take, I don't know, the whole drive. You encrypt it with that key, and then what do? This is the question. Where do you put the key? Think about your own iPhone. Where is the key? Where is the key stored? The encryption key for your iPhone. Yeah. Yeah. But so it's like kind of there's two contradictory things going on. One is you need to be able to get at your data using your PIN. And the other thing is if someone doesn't have your PIN, they shouldn't be able to get your data. So the key has to be stored in the phone somewhere, but has to be accessible only to the person who knows your phone screen lock PIN. Yeah, so let me kind of write this out and hope to try to explain why it's not so easy. So the basic idea is the one that we just discussed. So you encrypt all the data. Some, I don't know, say 128-bit AES. And it's a little bit more complicated than this, and I'll describe it in a second. And the kind of major question is where do you store the key? Yeah, so kind of two things to note. You cannot use the PIN. You know, your 4 or your 6-digit PIN. Yeah, because most people's PINs are, say, 6-digit decimal numbers. So it's like 10 to the 6 pins. And this is something like, I don't know, 20-bit. This is like would be a 20-bit key, where we want a 128-bit key. So 10 to the 6 digits, 10 to the 6 pins is the space is way too small to derive an AES key from that. Yeah. So that's one question. And the other thing is you can't store. The other thing you could do would be you can't store the PIN in, say, the flash memory somewhere on the phone, because this is the whole thing we're trying to prevent. Someone takes your phone, they look at everything that's stored on disk and try to decrypt it. So you can't store the pin next to the data because then you can just, or you can't store the AES key next to the data because then the person who steals your phone has the AES key. So sort of not so easy to see how this works. Do I use this board over here? So the architecture that Apple uses is pretty clever. So let's see if I can draw it like this. So on the phone, on the main chip that's doing the processing, the system on chip, there's this application processor. They call the application processor, which you should think of as like the CPU that's running your apps. And that's somewhere here. Outside, there's this like flash storage that anyone who steals your phone can look at. There's also the the RAM is out here that anyone with kind of probes while the phone is looking when the phone is running can look at. And there is a special AES engine that's separate from your application processor that when the phone is on and say running and decrypting data has a key, has an AES key in it. So the application processor actually talks to the AES engine over some bus, and the data that's written out to disk is encrypted using this AES engine with this key K, which I haven't told you where it's stored yet. But kind of one interesting feature already is that the hardware that's doing AES and the key is separate from the application processor. So even if you escape the sandbox that the app is running in, it doesn't immediately give you access to the AES key that's being used to encrypt the data. So that's the first thing. But then we still have to talk about where this key K is stored and how this relates to the pin that you use to unlock your phone. So the idea is we're going to have a special separate piece of hardware on this chip that will be responsible for managing these keys and helping.
Sorry, you said you call that a chip?
This is the SoC.
Oh, okay.
Yeah. Yeah. So there will be one component that's on a separate chip, but yes. So right. What was I going to say? Okay, so there's a separate thing on the same chip called the secure enclave. And the idea is that this secure enclave can communicate with the application processor over some bus. It can also communicate with the AES engine, and it can also communicate. Yeah, I guess it also has a communication channel to some special extra storage outside on a different chip. So let me kind of describe how this is useful. So the secure enclave does a few things, but one of the things it's responsible for doing is responsible for maintaining in a certain way the AES encryption keys on this device. This secure enclave is really in some ways its own processor, separate from the application processor. So it's, for example, running its own operating system. It uses its own version of secure boot, separate from the application processor. So when your phone boots up, there's two instances of secure boot happening. One with the application processor booting into iOS, and one in the secure enclave booting into this thing called XecOS. And so there's two different boot ROMs that are in this phone, and these two processes happen almost independently. In addition, there's a bunch of other stuff going on. So for example, it also uses measured boot. So this is kind of from Nikolai's lecture, the secure boot. And this is from Srini's lecture. So this measured boot, if you remember, when the machine boots up, the hardware measures the code that's running, and based on the code that's running, derives some encryption keys, which is given to the operating system once it boots. And if there's a different operating system running, the hardware is going to give you different encryption keys. So this kind of ensures that you only get the cryptographic keys that are accessible to the operating system are bound to the code that's running. So if someone tampers with the code that's running on the secure enclave, these encryption keys are going to be different, and you won't be able to decrypt anything. So this is to derive some kind of long-term encryption keys. And in addition, this enclave generates a random key on first boot, which is called the UID, the unique identifier, and uses this in addition to encrypt the stuff that and this uses, in addition to the key from this measured boot process, to encrypt, or say to derive its kind of device secret. Yeah, so on the first time you boot up the phone, the secure enclave picks a long-term secret. It kind of burns it into itself using fuses. This measured boot process gives another kind of secret that the secure enclave uses. And then on, it actually gets more complicated. So let me see it. Say one more thing, and then I'll pause to kind of take us back to explain why we're talking about this. This enclave, it also communicates with this AES engine over a separate bus. So the secure enclave to AES engine communication happens independently of the application processor. So all the keys, I guess the picture you should have is all of the keys are ever handled by the secure enclave. And when the AES engine needs to decrypt something, so the application processor says, I want to read a particular file, the secure enclave can send this key over to the AES engine and say, here's the key I want you to use. The AES engine can read the encrypted file from flash storage, decrypt it, and pass it to the application processor without the key ever leaving this AES engine. So even if an application escapes, sort of is able to compromise this operating system on the application processor, it still can't get at these AES keys, which, if you compromise the operating system, you can still get a lot of stuff. You can still get credit card information, you can get passwords, but these kind of longer term secrets are not going to be available to you. So, right. So I still haven't told you how we get from a pin to a key, because there's even more pieces going on than that. So the last component here that I want to mention is there's actually some external, what's called secure storage. that's sitting off the chip that communicates with a secure enclave on over some bus. And these guys, the secure enclave and the secure storage, because someone who gets a hold of your phone could potentially observe this communication between the enclave and the secure storage. These guys actually share a separate key. So I'll call it K sub S. So during the factory provisioning process, before the iPhone leaves the factory, there's some process by which these two sort of same random key is put into both of these devices. So later on, if someone tries to look at this communication or tamper with it or intercept it, they won't be able to, because this is using kind of AES encryption, encrypted pipe. Okay, so the last thing we need to do is see how the secure storage works and then try to put all the pieces together. So the enclave communicates with the secure storage. This is off chip. Using shared secret set in the factory. And the secure storage holds a few things. So the secure storage holds, and this is obviously going to be a gross simplification, but an encryption key for the user data. It holds, say, hash of the UID and other secrets. Call these enclave secrets, and the password, user's password or PIN. And it holds attempt counter, which is how many times you've tried to guess your PIN. So what's going on here is when you turn on your phone, it asks you for your PIN. I guess this is the screen. You're going to type some PIN in. The PIN is going to end up in the application processor. The application processor is going to pass it to the secure enclave and say, hey, please log me in. Here's my PIN. The secure enclave doesn't know the PIN. Secure enclave doesn't even know the hash of the PIN. So it can't check the PIN. What the secure enclave will do is it'll talk to this secure storage over this secure channel. So the secure enclave will derive, and I'll write this out in a second, but the secure enclave will derive the hash of the PIN using its secrets in its brain. Send that hash of the PIN to the secure storage. If the PIN is correct, the secure storage will return this encryption key to the secure enclave, who can pass it to the AES engine, who can decrypt your data. So it's like a lot of steps just to get from a PIN to an encryption key. This would be so much simpler if we just remembered 128 bits, but because we don't, you have to add all this hardware to protect against attacks. So now the question is, the whole point is we're trying to protect against brute force PIN guessing attacks, right? This is the problem. There's only 10 to the 6 pins, so if someone can sit here and guess all 10 to the 6 pins, they can get your data back. So somehow we need to set this hardware up so that that attack is difficult to do. Sorry. Yeah. So let me explain how that works. And I guess the main trick, there's kind of one main trick here that makes it possible. And that is that if you believe the secure storage is really secure, what we can do is have every time there's an authentication attempt, the secure storage will increment this attempt counter. And after, say, 10 authentication attempts that fail, the secure storage can securely delete the decryption key that's going to let you get the data back. So as long as you trust that the secure storage is doing its job correctly and its state can't get rolled back, and an attacker who steals your phone can't see into the brains of the secure storage, it's going to be really hard to guess more than 10 pins incorrectly without getting the data wiped. Yeah. So that I have no idea why they designed it this way, but maybe you know.
It's manufacturing. It's a very, well, the technical reason, but really nothing to do with security. The manufacturing process that's used for flash and EEPROM and non-volatile secure storage is very, very different from the process that's used for processors. And so integrating flash or non-volatile storage into processors, it's difficult. It's just an economic problem.
And do you know, Srini, like how reasonable is this to think that you can have this type of secure storage that you say can't read in? Is it more?
It's a level of maybe better than smart cards, you know.
Yeah.
I think it's probably breakable. I mean, I mentioned you can go to Chipworks and delayer this and so on and so forth. I can imagine the FBI has ways of covering that.
Yeah.
But it's money, and it's for attack. So it's if you discover a secret key for a particular phone and it costs you $100,000, you would need to spend another $100,000 for a new phone.
Yeah. And it seems like people prefer to break the software.
No,
I guess the hardware has gotten difficult enough to break. So okay, let me run through this protocol. So this is PIN kind of authentication with the secure enclave. So okay, step one is user enters PIN. Then this iOS on the application processor passes the PIN to the enclave. The enclave, through methods that that are not specified, at least in the design docs that I was able to get my hands on, the enclave tries to enforce some kind of timeout. So after you guess a PIN wrong 5 times, it's going to make you wait longer and longer. And what Apple says is it's going to be impossible for you to speed up PIN guessing, even if you reboot, power off, and power on the phone. So my guess is how this is implemented is that the secure enclave has some kind of clock in it that reads a kind of a bit from the secure storage that says, did I wait long enough yet? And the secure enclave will run its clock for whatever, 30 minutes if you're supposed to have a 30-minute timeout. And once it runs 30 minutes, it'll set the bit in secure storage that says I waited long enough. And if you reboot the phone, this timer is going to start over. So this is how, even if you power off and power on the phone, the idea, I assume this is how it's implemented, is that you can't speed up PIN guessing, even if you're guessing a few times. So the enclave enforces some kind of timeout like this. Then the enclave passes the hashed PIN to the secure storage. And the secure storage checks the PIN in the following way. So checks the PIN hash. So if correct, meaning it matches this second value up here, you return the AES key. And zero out the counter. Otherwise, increment counter. And if you made too many guesses, if counter is too big, say you get 10 guesses, erase the key. So this, I don't know if this has ever happened to you. In college, my friend left his BlackBerry. This is back when that was a company. BlackBerry on the couch, and I was just having fun trying to guess his PIN. I guessed like 6 times, and then the phone says erasing. And then And then I got really nervous. Yeah. This is a former friend of mine. Oh yeah, does this happen to you? It was really this. There should be a word for this emotion that happened. Yeah, but yeah. So with iPhone, it'll really erase. And the way it does it is this secure storage. Right? Apple designed this hardware, and one of the ways they designed the hardware is to normally flash erasing stuff on a computer is basically impossible, securely erasing, because usually when we erase, we don't really erase, we just kind of erase some pointer and the real data is still sitting there. Here, they're really addressing this little, whatever's doing the processing in here is really able to address the flash and is really able to try to write garbage into whichever piece of the flash is storing your keys. And this makes it supposedly very difficult to recover this stuff that's been erased. So they call this effaceable storage. And so if this succeeds, then the Enclave, I guess I won't write these last steps. If this succeeds, then the Enclave gets this AES encryption key back, passes it to the AES engine, which can decrypt the stuff. So let's just think about why this design prevents some of the attacks that someone might try to run. And I don't know if you're, yeah. Yeah. So this is I think comes down to how big the physical components here actually are. But my sense, and Srini can give us the real answer, is that these wires are actually quite large and are big enough to like stick a measuring probe onto the wires that are crossing these package boundaries.
SoC stands for system on a chip. So that chip, as Henry said. So there's secure storage is a separate chip. And it's usually like a little bit like a smart card chip. It's usually much smaller than the system on the chip. And the idea is that there's usually a low pin count and fairly low bandwidth connection between these two. And so that's relatively easy to probe. And so you can't have KS moving across exposed. You can't have you can cap that. I mean, it's not as bad as the Xbox used to be, where they actually had something like that. A little big piece of the original Xbox that was broken by actually this MIT student called Bunny Huang, like 20 years ago. That was a low pin count bus and a secret key stored in this little chip, and that secret key was the same for all Xboxes, and it was sent over to the bus to the processor. So it's a very similar scenario, and that was $100 today.
Yeah. So I think it's a matter of size, yeah, basically. Because Srini, like the thing that you would need to probe to get the key out of here, my understanding is it's both very small, but also you can kind of dump this whole thing in epoxy, physically protect. It's easier to physically protect these smaller, say, secure storage than it is to protect the wires that are going across. But this is all, I mean, I guess, well, okay, yeah, I'll come back to it in 1 second, but I think these things are all about raising the cost, because in the end, the key is somewhere in there. Just about, the phone can get it. So if you're clever enough and you spend enough money, you can also get it too. I think it just, yeah.
Why is the UID?
Because the secure storage, I think, isn't supposed to know the UID. But yeah, I mean, there's kind of defense in depth going on here. So you could also ask, like, why even bother hashing the pin? Like, yeah. But I think the idea is, even if you break into the secure storage, even if you extract all the stuff, you still don't get the pin. So if you used a really long pin, which you can on an iPhone, you can use an alphanumeric pin that's as long as you want, I think, then you don't get so. I mean, they're really going layer on layer on layer on layer. So, okay, so let's see. This defeats, many attacks that you might try. So let's just check that some of these attacks don't work. So brute force pin guessing attack. What's going to happen if you say compromise the application processor completely? Is the secure storage counter thing is going to prevent you from doing a brute force attack, because after 10 wrong guesses, the secure storage is going to erase the secret key. So this is going to be impossible as long as you can't break into the secure storage and tamper with its counters. Another thing you might try to do is you might try to replace the secure enclave with a backdoored one. Yeah. So as we said, these wires are big enough. You could just pull off, one secure enclave chip, put on a different secure enclave chip, and try to talk to the secure storage that way. So if this KS was common to all of the iPhones, that would, you could do something there. I guess you could, but I guess still, you can't even talk to the secure storage with a different secure enclave, because this communication channel is protected by KS. So this doesn't really help you. Not clear how that would be useful to you. I guess even if you, took someone's phone while they weren't looking, you swapped out the secure enclave chip, and then they entered their PIN, still this wouldn't help you, because the secure enclave chip that you put onto their phone couldn't even talk to the secure storage, because KS is going to be different. So even in these kind of crazy settings, this is not going to, the new secure enclave chip that you put on won't know UID, won't be able to, these things are all bound to each other. And the other thing we talked about is guess the PIN and, and reboot. This also won't work because the state is sort of persisted across reboots. This idea of using the secure storage to allow sort of really erasing cryptographic secrets is actually used in modern iPhones, the latest version, for all sorts of things. So it's used to erase if you put a credit card number into Apple Pay and then erase that credit card number. That erasure is happening with the same secure storage. So you'll encrypt, the phone will encrypt your credit card number with a key that only the secure storage element knows. And then when you want to really erase the credit card number, the secure enclave can just tell the secure storage, please erase this key for me. And then that credit card data will still be on your phone encrypted, but with a key that nobody knows. So that's kind of cool. It's used for, I guess, Face ID, Touch ID, a bunch of places where you want to erase something. Yeah.
The only two components that are assumed to be secure or intrinsically secure is the enclave and the storage.
Even for the purposes of this.
Or I guess, for example, the AES engine.
Yeah.
This one can kind of look into what's happening there. Or
I think it depends on who's looking. So for example, I think in the context of a hardware attack where someone has hold of your phone, I think the AES engine, yeah.
someone has, yeah, exactly. That's what I was asking. Someone has pre-sold my phone.
Yeah.
Is able to kind of open everything.
Yeah.
He can see everything except for the secure enclave and the secure storage.
I think that's certainly sufficient to get what we need. I mean, it may be also difficult to extract secrets from the AES engine.
That's kind of what we're assuming.
Yeah. So the reason to separate out the AES engine from, I guess, the reason to separate out the AES engine from the secure enclave and have it set up this way, I think, is performance. But the reason from a security perspective why the AES engine isn't just inside the application processor is that key is never exposed to the operating system. So the operating system can't accidentally leak the key or through some side channel attack leak the key. I think there's physical isolation there is one way that they try to get security. Yeah, good. Okay, so if you've used an iPhone, you know that you don't actually have to enter your PIN every time. You can use Face ID or you can use Touch ID, right? So how does that work? Well, always when you reboot the phone, you need the PIN. So when you reboot the phone, all the secrets in the secure enclave that allow you to decrypt your data get wiped. But otherwise, the PIN is actually, or the encryption keys are stored in the secure enclave. So that's how you can get these things back using Face ID or Touch ID. However, there's one kind of additional thing attack that you might worry about, which is you leave your phone at a restaurant, you have Touch ID enabled. So this is the fingerprint reader that lets you unlock the phone. And somebody pulls off the fingerprint reader on your phone and puts on their own fingerprint reader and basically feeds in an image of your fingerprint that they got from the wine glass or whatever into the secure enclave, and thereby unlocks your phone. Does that attack make sense? Like, how does a secure enclave? So if this is the fingerprint reader, which is definitely not in this chip. The fingerprint reader is off the chip. How does a secure enclave know it's talking to a fingerprint reader and not just some bits that you fed in be, a fingerprint image that I got off of your wine glass? Does it attack? Yeah. Yeah, and the answer is that these guys also share a secret. This is like K fingerprint and K fingerprint. So that there can be an authenticated channel actually between the secure enclave and the fingerprint reader. So each time we do this, we've added like $30 to the phone. So it's like the iPhones are expensive in part because of Tim Cook's airplane, and then in part, it's like 50% the airplane and 50% all this stuff. It's really expensive, I think, to manufacture. Have all these components synchronized, it seems like a huge pain. But I guess one thing to take away from this is a much weaker type of security than what happens when the phone is powered off. So if you're really worried about it, you would power off your phone. All right. So I wanted to mention kind of another cool thing about this architecture that relates to this jailbreaking we were talking about before. And so one kind of interesting feature is that we now have these two processors on the phone that have their independent trusted boot processes. And when the application processor's boot ROM was buggy, which is what allowed this check rain jailbreak, the secure enclave could actually help us or help Apple prevent this kind of jailbreak. So let me try to explain what I mean. And I guess why is this interesting? Well, I guess it shows what the power of having this separates one of the ways in which a secure enclave can be helpful for security, at least from Apple's perspective. So this is kind of an aside, but how a secure enclave can be helpful. So with that check rain jailbreak, the user exploits a bug in the application processor. So boot ROM to install, an OS, non-Apple OS on the application device. And this is unpatchable because the boot ROM is wired into the processor. So on the new phones, on say this like A10 and beyond phones, the enclave knows whether it was booted, whether phone was booted via USB. So if you remember, this attack relied on you plugging your phone into the USB bus on your computer and feeding an image and then somehow tricking the phone into booting that image. But the secure enclave actually has enough information about the boot process to know whether it was booted from kind of the normal way or from this diagnostic USB way. There's a bit in the secure enclave that tells it which way the phone was booted. And what it can do is what Apple told these newer phones to do is just never decrypt any user data when in this kind of debug mode when booted in this debug mode. So if you boot the phone, the secure enclave knows that you've booted over USB. You try to decrypt some file, and the secure enclave is gonna cause the phone to crash. It'll say the only thing that you can do in this mode, you shouldn't be looking at users' data. All you should be doing is loading a new operating system and then rebooting into that operating system. So what happened is, although the application processor couldn't be updated, the boot ROM there couldn't be updated, the boot ROM on the secure enclave was still correct, and you can update, you can change the bootloader or the operating system running on the secure enclave. So I guess you could patch one even if you can't patch the other, which I thought was kind of an interesting feature here. But then, of course, turns out there's also a bug in the enclave. Later discovered, which allows you to bypass this too. So this is why you should always buy a new phone. Yeah, and it was also, you could ask how did people find this bug in the enclave? Well, turns out, I'll say it, yeah, because this is just interesting to see how these things are manufactured. Turns out the secure enclave doesn't have, also needs to talk to RAM. It has to store stuff. And it has its own encryption engine. And when it writes stuff to RAM, it encrypts it first using some AES key and then writes it out to RAM. But when it's first booting up, there's some stuff it has to write to disk to RAM that's not encrypted. And it turns out there was a way that someone could figure out how to exploit this to actually execute arbitrary code on the secure enclave, which then game over. So okay, that's a lot of stuff about enclaves, but I hope it was helpful. So in the last couple of minutes, I want to talk about just where could bugs remain, and then I guess what other bits do you need to put together to make this work? Actually, maybe I'll talk about the second thing first. I'll just say it. So where bugs could remain here, this is obviously not perfect. So the kernel on this application processor, the operating system here is big and can have bugs in it. So even though the application processor never actually sees the AES keys, it still sees your credit card number, still sees your photos, still sees your passwords and so on. So if you can start running arbitrary code over here, malicious code over here, you can still do a lot of damage, even if you don't get the kind of long-term AES keys. As we mentioned, these boot processes, secure boot, trusted boot on both of these processors can have bugs, do have bugs. Then the other thing is you can kind of break the assumptions we were talking about. So if you spend enough money, right, you can extract secrets here. You can even use side channels potentially, so timing information or other types of side channel attacks that we haven't really discussed, potentially to read data that you shouldn't be. So these could be, one application can read another's application's data, all sorts of stuff like this. But I would say that having these isolated components like this, really physically isolated, makes side channel attacks much, much more difficult than they would be on a normal computer. So those are some things that still could be problematic. So I'll just briefly say that why this ends up being even more complicated when you want to implement it in the full system. So we discussed kind of going from a pin to one AES key. But really, there's a huge number of things that need to be encrypted. And for various reasons, you might want to use different AES keys for them. So there's actually an entire hierarchy of keys that your phone derives when it's running. So there's kind of a sort of a main key, main device key, which is the one that you get when you enter your PIN. There's also these encrypt what are called class keys. So for different types of things. So some files on your device are only available when the phone is unlocked. As soon as you lock your phone, those keys are erased from the secure storage's brain. There's some devices, some files on your phone need to be writable even when your phone is locked. So for example, if someone sends you a photo and your phone is locked, you should still be able to put that photo somewhere. So there's a bunch of other stuff here, like I don't know, append some types of encrypted files you can append even when the phone is locked. And there's some things that are only encrypted when the phone is kind of off. So it's like you can read write when booted. So basically each file is encrypted with a key. This is like a per file key. And then the profile key is encrypted with one of these class keys. These class keys are either kept in memory or not, depending on which type of class they are. And those class keys then are all encrypted with this main device key, which is then protected by your pen. So it's like really complicated to make this thing work. But also, if you're interested, it's totally worth reading about. It's like fascinating design. So, okay, I think I'll stop there. I guess just the thing to maybe the takeaway from this lecture is, first, you should know secure boot. It's like a super interesting, super useful technology to prevent against certain types of tampering with the operating system. And defending against these hardware attacks requires a lot of sophistication and a lot of cost to do well. And it's like a very difficult kind of attacker, an attacker that has your phone in its hand and is going to stick probes into it and so on. And I think the game here is about raising the cost and coming up with designs that raise the cost without raising the cost of the phone too much. And maybe the last thing to say is this principle of isolation that we've talked about is used at many layers in a device like this. Like there's many types of isolation going on, which is the same principle to isolation in crypto over and over and over and over and over. And that's how you build an iPhone. So any two things you should remember are isolation and cryptography. Cool, that's it, thanks.